Hello, hello. What I am going to do is talk about the photon model of radiation in relation to particles. This is on AQA, A level, and it's from the section 3.2.1.3. Right, okay. So, in terms of the link to the EM spectrum, what we should remember from our GCSE is that a wave's behaviour depends on its frequency or wavelength. At the long wavelength section and things with low frequency, we have radio waves, then followed by microwaves, then followed by infrared, then followed by visible light, then followed by ultraviolet, X-rays and gamma. And if you have forgotten how to remember the order, then we can use the mnemonic rich mice in love for light use extra gel. So rich mice in love use extra gel, apparently, allegedly. Right, okay. So this is the end where you've got long wavelength and low frequency. At this end you've got short wavelength and you've also got high frequency. Now the end of the spectrum that's causing cancers, etc., is this end. So UV from sun's rays, X-rays and gamma are all things that can cause cancer over a period of time. This is the end where we've got the most energy. So there are no known deaths due to radio waves. There are known deaths due to gamma. Right, okay. So what we can do is we can say that energy is proportional to frequency. So if you increase the frequency, then you increase the energy. Now, in order to get our heads around this a little bit more, we need to talk about the photon model. Now, what the photon model is to do with, it's to do with waves with properties of particles. Okay, if you want to look into this a little bit more, then I suggest you look up de Broglie wavelength and wave-particle duality, which comes up on the quantum phenomena part of the course. So if we imagine a particle instead of a wave in the same circumstance, then it will have frequency because it will be vibrating about a fixed point. So like a pendulum, it will go to a point of maximum displacement and then it will return to its equilibrium position, and then it will go to its maximum displacement in the other direction, and then like that pendulum it will return to its equilibrium position. So what we have got is a wave, okay, where we've got rest position, maximum displacement, back to the rest position, maximum displacement in the opposite direction, and then back to the rest position again. Okay, so in terms of the photon model, if we were to plot a graph, and I will do it properly, you'll talk about threshold frequency and work function more in quantum phenomena. If we've got energy on this axis and frequency on this axis, then we've got a positive correlation. So when energy increases, frequency increases as well. Right? Okay, if we were to look at that gradient, then energy divided by frequency will give you a constant known as Planck's constant, which is 6.63 times 10 to the minus 34. And I'm going to let my daughter in. Come here. Come in, I'm teaching. You sit there and watch if you want. I'll pick the coat hanger up later. Right. Okay. So energy divided by frequency equals to Planck's constant, which we give the letter H. So in terms of E is proportional to F, the proportionality constant there is H. So we say E equals H F. Right. There's a little bit more to it than this. What we must remember from our GCSE is the equation V equals F lambda. What we refer to it as at A level is C equals F lambda, where C is the wave speed, F is the frequency, and lambda is... Why doesn't it do plus? Yeah. It's multiplying. It's multiplying. You've got times 2 together. You don't do a lot of adding stuff together at this point, darling. Is that all right? Is that okay? Right. Okay. So, if I substitute this in for F, we can see that F is equal to the wave speed divided by the wavelength. So if we substitute this into this equation over here, energy equals Planck's constant times by the wavelength, times by the wave speed divided by the wavelength. Okay, just a few more things to consider. You could be asked to convert in between electron volts.
Daddy,
Yeah.
what's that thing for?
That is for X-rays. You know, like when you broke your arm or something. Yeah. All right. Thank you. Thanks for getting involved. I do appreciate the feedback. Okay. So, in terms of this equation, what we also may need to take into account is the energy values that we'll get for this will be quite low. So we convert into electron volts. So 1.6 times 10 to the minus 19 joules is equal to 1 electron volt. Typically, we may see values such as mega electron volts, mega being times 10 to the 6. So that's 1.6 times 10 to the minus 13 joules is equal to 1 mega electron volts. I wish it was equal to 6, darling. It would make things a lot easier. So, if I go through an example, if we've got the wavelength of red light from a helium neon laser, which is 4 parts helium to 1 part neon, that is 632 nanometers. Not a value you need to remember, but if you're doing any calculations, it may come in handy. So, what you would do, if we were calculating the energy is equal to...
Can I do my favourite colour that's on the board?
You can do your favourite colour that's on the board once Daddy's finished talking about Planck's constant. I'll tell you what, you colour on that bit of the board in the corner while I carry on. This is going on YouTube, so you know, you might be famous, you might not. Right, depends if it goes viral or not. Right, so 6.63 times by 3 times 10 to the 8 divided by the wavelength, that is 632 times 10 to the minus 9. So, that is a squid.
No, it isn't.
Well, what is it then? If
A
it's not...
monster.
Well, what type of monster? You need to be a bit more specific. Times 10 to the minus 34.
It's a round scared ghost monster.
Oh, yeah, it is a round ghost monster. I can see the resemblance now. So, I put that on the top. I put 632 times 10 to the minus 9 on the bottom. That's the spec gone west. Okay, and that gives us an answer at 3.14 times 10 to the minus 19 joules. If we're asked to convert that into electron volts, then we simply divide by 1.6 times 10 to the minus 19, and that gives us 1.96 electron volts. And that, ladies and gentlemen, with the assistance of a 5-year-old, is the Photon Model. Okay, if you have any questions, feel free to get in touch. I'll leave the last word to my daughter. Go on in, Octavia, what are you doing now?
A road.
You're doing a road. Fantastic. The road to success. All the best.